So now we review the basics of a vector on the Bloch sphere. Now we will then go into the density matrix, right? How is it related to the Bloch sphere? So before we do that, just think about what is the density matrix of a qubit. Now it is easy because it's a qubit, right? So because it is a qubit, all I need to do is just that, let me write down the equation, rho equals to summation I equal to 1 to k, p k I. This k still can be very large, can be 1 trillion. Pi. I keep doing the wrong. Thank you. Right? Still can be a lot, right? Not because it's qubit, then we only have 2 pure states. We have trillion of them, right? And again, it still obeys this relationship. The trace of the rho must be 1. And it is also positive semi-definite. And I'm going to use this definition. It is Hermitian, and all its lambda eigenvalue are larger or equal to 0. So now all we have learned will become useful. What is the size of the qubit, the matrix, if it is a qubit? What is the size of this matrix? What is the size? 2 by 2, thank you. 2 by 2, because you only have 2 basis states, right? This is the stuff. So rho is just like the M we discussed earlier, the general M. It can be decomposed into A0I plus AX sigma X plus AY sigma Y and plus AZ sigma Z. Right? We spent a lot of time to discuss the space formed by the Pauli matrix and the identity, right? They are just a linear combination. Is that okay? And I can write it as A0I plus A vector dot product sigma. I can write in that way. Now, however, because of the math, I decided to change it a little bit. I'm going to call A0 dash equals to 2A0. Okay? And then A dash equals to 2A vector. I just have scaled it. I just use another constant, right? Make it 2 times. Then this equation, rho, is going to be A0 dash I plus A dash dot sigma divided by 2. For some reason later. All I'm trying to do is just to make it divided by 2. Okay? So from now on, this is just to connect you to the old derivation. If you forget the old derivation, basically, again, you just said I can write rho as 1 over 2 times this guy. You can call it A0 or an A. You don't need to use dash if you don't like. Okay? But in this class, we communicate in this way. Right? So is that okay? Nothing special. Just repeat what we've done before, right? Okay. But what is A0 dash? Do you remember how to find A0? Very good. Inner product, right? I times M, right? Which is rho. What is the trace of rho? 1. Right? And similarly, for others, for example, I call it I equal to X, Y, Z equals to, I think I missed something. Sorry, actually this should be, A0 should be half, right? I forgot to divide by 2. Should be divided by 2. right? And then AI is also half of trace of sigma I times rho. Okay? Now, this one we need to evaluate. This one we don't know. But the main point is that eventually you will get rho equals to, because now you say A0 equal to half, then A0 dash equal to 1, right? So this is equal to I plus A dash dot sigma divided by 2. Okay, so all the density matrix of a cubic can be represented with an identity plus A dot sigma divided by 2, which is not surprising. Okay?
What happened to the half? A0 is 1/2. Oh.
Because now I use A dot, right? A0 dot. Because A0 is 1/2, so A0 dot is 1. Okay? And from now on, you can call this A. It doesn't matter, right? As long as you put the right number, right? So let's take a look. The pure state on the Bloch sphere. Remember, now we get the density matrix. It's just the density matrix and nothing to do with the Bloch sphere, right? But we know that if it is a pure state, let's look at this. Okay, let me write the equation here one more time. Rho equal to I plus A dash dot sigma divided by 2. Okay? Let's see. I'm going to say that if A magnitude equals to 1, then it is a pure state. Okay? So if I have a density matrix, and then I express it as I plus A dash dot sigma divided by 2. If I get A equal to 1, then this is a pure state. Okay? So I can try to prove it. That is because rho is going to be equals to 1/2, the whole thing, right? 1001 plus A dot sigma. What is A dot sigma? It's just equal to AX sigma X plus AY sigma Y plus AZ sigma Z, right? I can put a dash to it if we want, correct? So actually I want to put a dash from now on. So this is what? 0 AX dash 0. Do you see this one? It's actually very simple, right? Because this is X is what? 0, 1, 1, 0, right? And times AX dash, I have this. This one. Let me show you one more time. AX dash times 0, 1, 1, 0. Okay, then how about the Y? What do you write? 0, negative, I, AY dash. I, AY dash 0. Okay, what I'm doing is just multiply this way. And similarly, what is Z? It's 1, but we multiply by AZ, right? Negative AZ, right? So I spell it out slowly. Actually, we don't need to, but I just want you to do it slowly. Then because of this, I get this is 1/2. What is this? This is 1 plus AZ, AX dash minus I, AY dash, AX dash plus I, AY dash, and then 1 minus AC. right? What I'm doing is just add up the elements one by one. And you should be very familiar with this without 1 already. We did that, I mean, in the previous class, but, right? Because z is on the diagonal, x, y are off diagonal, right? So you only have ax minus iay, ax minus plus iay. One thing you can do is do the square and then find the trace to prove it, right? Another way is I decide to find the eigenvalue. So we take this opportunity to review how to find the eigenvalue, which you probably know already, but you need it in the homework. Yeah, we use the determinant, right? When you find the eigenvalue, your goal is to do rho minus lambda I needs to be 0. Okay, so what does it mean? It means I'm going to ignore the half because it's 0. No, I cannot do that, of course. Can I? Well, I can do that because then because I have the then I need to multiply lambda by 2. Yeah. So let's do this, right? So still the determinant equal to 0, but I'm going to just spell this out so that you can see it. This is 1 plus az dash minus 2 lambda. Let me erase this. Right, and then my cheat sheet was wrong. So ax dash minus iay, and then ax dash plus iay, and then 1 minus az dash minus 2 lambda. This whole thing needs to be 0. Do you see this? So this is the original matrix, right? I multiply by 2, then I think I did something wrong, maybe. So I better be careful with this matrix. So let me don't multiply by 2 lambda. I actually need to divide everything by 2. That would be better. Okay. Yeah, this is something I always make, the mistake I always make. Determinants cannot just do multiplication, right? Unlike the matrix, right? So is this, this is messy, but is this clear? Any questions? How I get to here? Right, I have the matrix, right? I am still using the matrix. I multiply half to there, and then minus lambda I. I is only diagonal, right? So all the diagonal subtract by lambda, right? So with this, then you say this is 0. Then basically I'm going to say this two term, 1 plus AC dash divided by 2 minus lambda times 1 minus AC dash divided by 2 minus lambda, and then minus the next term, right? But this term is what? Just something plus something times something minus something, right? So this term is just equal to ax squared plus ay squared, because there's an I squared, right? And then the whole thing divided by 4 equals to 0. Right? And the 4 can be cancelled similarly. For this term, I have this a little troublesome. 1 minus 2 lambda plus AC, 1 minus 2 lambda minus AC, right? So this term is just equal to 1 minus 2 lambda square minus AC dash square minus ax square plus ay square equals to 0. Okay? right? So with this, then let me see. Because we say that this is equal to 1, right? You add together equal to 1. So with this, then you have 4 lambda squared minus 4 lambda equal to 0. So lambda equals to 0 or 1. Do you see this? Because this is a 1, right? The whole thing is 1. As because we say that the magnitude is 1. Right? This basically saying that ax squared plus ay squared plus ac squared equal to 1. Right?
Ax squared dash ax.
Yeah, so here I kind of mess up all the, you just remember ax equal to ax dash, right? Ay equal to ay dash, and then ac equal to ac dash in this page, okay? On this page. So this one I have 4 lambda squared minus 4 lambda, right? So lambda is going to be 1 or 0. So the eigenvalues are 1 or 0, then what does it mean? When I diagonalize it, I get 0 or 1 on the entry. Right? This is a little bit difficult to say. Sorry, it's not clear. 1, 2, 3, and then 4. It means that the matrix, after diagonalized, is either 1, 0, or, 0, 1 or 1, 0, right? So is this a pure or mixed state?
Pure.
It's a pure state, right? So here I show that if the length is 1, I get a pure state. And a pure state, of course, it must be on the Bloch sphere. Right? So the whole message in here is that if you have a pure states, then they are on the Bloch sphere. Its corresponding density matrix must have A equal to 1, the magnitude of A equal to 1. So when you decompose it, you will find that you have the length of the A equals to 1. That is a pure state.
So I think that's what you were saying the other day when I was asking if there's any rules in constructing the states. You can have a lot of states, but you cannot just haphazardly say 50% 0, 25% 0 plus 1, and
From the density matrix, you cannot say, yeah. But now we're talking about pure state. What I'm trying to say, if your density matrix is represented in this way, I plus A dot sigma divided by 2, if your A has a length of 1, it is a pure state, and it is a state on the sphere. Okay? Then you probably can guess now, what if it is a mixed state? It's going to something inside this block, not surface, but the inside, the body. Okay? But before that, let's try to understand something more, right? What is the expectation value of a Pauli matrix? What's the expectation value? We know that, for example, I have a wave function psi, and I want to know what is the expectation value of psi of sigma c. Sigma c is something related to the spin in the z direction, right? We accept it is, right? We did not go to quantum mechanics or any discussion yet. We will do that later. But now I accept that this is the expectation, this is the operator. And then what is the expectation value? Again, you will just go through this math, right? This sandwich to find the expectation value. How do you do it? Remember what is psi? Alpha 0 plus beta 1. But now we will have the Bloch sphere. We are going to make it easier, right? Cosine theta divided by 2 e to the power negative I phi divided by 2. 0 plus sine theta divided by 2 e to the power phi divided by 2, 1, right? So this one I need to find the bra. What is the bra version? I'm going to use the matrix notation. What is the bra version of psi? Cosine theta divided by 2 e to the power plus, I forgot the I, sorry, plus phi, I phi divided by 2. Sine theta divided by 2 e to the power negative I phi divided by 2. Multiplied by z, which is 1, 0, 0, negative 1. And then cosine theta divided by 2 e to the power negative I phi divided by 2. Sine theta divided by 2 e to the power I phi divided by 2. Right? Yeah.
Wouldn't it be easier if you just use alpha beta and just do the math and then?
No, because there is, okay, maybe you can do that, but then our goal is to look at theta and phi. Then you need to convert back. The reason I'm doing this is that I want to show you the expectation value is related to the Bloch sphere. Okay? So you do the multiplication. The first term is easy, right? Just this, multiply this one. What do you get? This, multiply this one. Cosine theta divided by 2 e to the power I phi divided by 2. That's it. Right? And then the second term is negative sine theta divided by 2 e to the power negative I phi divided by 2. Right? And then multiply this term. Right? That's how you do the expectation, right? Then when you multiply the last term, it becomes what? Cosine square theta divided by 2. But this e to the power I phi divided by 2 cancel with e to the power negative I phi divided by 2. E to the power negative I phi divided by 2 cancel with e to the power I phi divided by 2 because you do multiplication with this one. So this term times this term plus this term times this term, right? So this one gives you negative sine square theta divided by 2. Right? And use some trigonometry, you see this is just equal to cosine theta. Because cosine square theta minus sine square theta equal to cosine 2 theta. Just the identity, right? Which I can never remember. But what so special about this? We already know how to find the expectation. The main point is that if you have a state here, you see the expectation value is what? It's just the projection into the z-axis, cosine theta. That is its expectation value. So now the Bloch sphere does have some meaning, some relationship to our real 3D space, right? Because psi does not really reside in the 3D space at this point. It's not like in front of me 45 degrees. It does not. But however, by using Bloch sphere, I imagine it is there and project it to the z-axis. It does give me the expectation value I will get when I do a spin measurement along that direction. Okay, so again, the psi does not exist in our 3D space. But turn out that it has some connection between our real 3D space, because theta is something in our real 3D space. It's not in the hyperspace, right? There's no theta in the hyperspace. It's something in our real 3D space, right? That we map to our 3D, right? So with this, then I want to go to a more general one. Then I wonder if you can think about what if I have a polyvector in this form? What is the projection of, what is the expectation value, right? Now, here I ask you, what is the expectation value for given psi? What is the expectation value of sigma z? There's an operator. Now, what is the expectation value of A dot sigma, which is important to us, as you can see here, right? What is the expectation of A dot sigma? Then you come up with an idea, because what is A dot sigma? A dot sigma is I have AX times sigma x plus AY times sigma y plus AZ times sigma z. Basically, it is this, AX, AY, AZ. sigma x, sigma y, sigma z. Dot product, right? And this is just a vector in our 3D space. Yeah? Isn't that it is? We can say that is a vector. In sigma c case, this vector is just equal to 0, 0, 1. It means vertical, yeah. Question? Okay, right? So let me just, let's talk about, I think I should inject this one. So if it is just equals to sigma c, that means what? A equals to 0, 0, 1, right? If it is sigma y, then it means A equals 0, 1, 0. If it is sigma x, then it's 1, 1, 1, 0, 0, right? But it can have other combination. So if I'm talking about sigma c is a projection onto sigma c, probably you will guess. How about the expectation value of y? Probably it's the projection onto the y-axis, right? How about for x? Projection for the x-axis, right? But how about I have a general vector, let's say pointing in this direction, which is A. Probably is the projection onto that A, right? That's what I'm guessing. And you can prove it. So I would then say the expectation value is A dot sigma xi. Okay, so I'm going to just give you directly. Actually, in the homework, I asked you to prove the results for x, for y, and x. But I'm going to give you the intermediate results. You will find that it is equal to ax sine theta cosine phi plus ay sine theta sine phi plus az cosine phi. This is the answer, okay? So in the homework, I asked you to prove this few things, because this one you can expand into sigma x, sigma y, sigma z. You just repeat what I'm doing here for sigma z, for sigma x and sigma y, then you will get these terms, right? Just prove it in your homework. So you will find that this just equal to this. Now, if I try to recognize this as, again, a dot product, this is what? AX, AY, AZ times sine theta cosine phi, sine theta sine phi, and cosine theta. Here is just a matrix multiplication, right? AX times this, plus AY times this, plus AZ times this, that is what I get. So what is this? This is the vector A. And this is just I call this xi. No, I call it a vector. This is not the state. I'm talking about the vector correspond to the 3D. This vector. Now in the 3D, I try to draw a vector. I call it xi, just xi vector, right? This is a 3D space vector. I map the qubit states to this point in my 3D space. And then at that point, I call this as a psi dash, right? This is exactly equal to this. You can try to think about this. For example, this one Z component is what? Cosine theta, right? Do you agree? This vector, Z component is cosine theta. How about X component? Is sine theta and then cosine phi, right? You project to equator and then cosine phi. X component. How about the Y component? Project to equator is sine theta and then psi phi, right? So I'm just saying this vector, our real 3D space vector, correspond to this state is just this, right? And I'm showing you that the expectation value equal to this one times this one, which is just the dot product between this vector and this vector. So that's the good thing about the Bloch sphere, right? None of the states really reside on this Bloch sphere. We just map it to the Bloch sphere. But each of the qubit states, we can come up with a vector, real 3D vector corresponding to it. Because we map it to a point, then there's a vector, right? And then its expectation value on this poly vector is going to be just the inner product of these two vectors.
And the A's are not complex, they're real 3D space?
Correct. Can A be complex? Do you remember when we do the decomposition, we say that if it is Hermitian, then all the coefficients will be real. At the very beginning, we talked about the decomposition that M equal to, this is good to remind everyone, right? A, Y, A, C, sigma C, right? So this space is formed by these four bases, very general. But if M is Hermitian, we say that A0, AX, AY, AC will be real, right? So because of this, A is always real, because the density matrix is, not that, this one is Hermitian. Sigma is Hermitian. Okay, so as a result, A is real, right? So it mapped to our 3D space very seamlessly. Answer your question?
Sorry, I was thinking sigma y. If we just have A0, AX, and AZ be 0.
Yeah.
And sigma AY is I. Doesn't that give a Hermitian?
Okay, we are saying that for Hermitian, give you a Hermitian matrix. No, Hermitian, you also need to
No, never mind.
I don't know what you're talking about. So you're saying that what if the matrix is,
I'm wrong. It won't be a Hermitian matrix.
it need to be conjugate, you're talking about this, right? Because you need to transpose, then it won't be the same. Yeah, you're right. It's not Hermitian. Okay. Now, so I hope you have this view that the expectation value is just a projection, right? If M is Hermitian, then A real. What condition? Oh, because he is saying that what if AY is I, right? And this one equals to 1, -1. But this is not Hermitian because you need to do the transpose, right? It is real but not Hermitian. Okay, so with this, then let's talk about the mixed states, right? So let's look at I think that's what I want to say, right? Yeah. So let's first look at a simple example. I have two pure states, right? One is alpha percentage, alpha part, right? I call it part, I don't call it percentage, of 0. I have beta part of 1, so that alpha plus beta equal to 1, right? I have a mixed state. What is the density matrix for this one? It's going to be alpha 0 outer product plus beta 1 outer product. Right? So if you write it in a matrix form, it's going to be alpha, beta, like this, right? You agree? Now, this one is easy for me because if you try to do some math, right, I'm not doing it, it's equal to I plus sigma z times alpha minus beta divided by 2. Okay, so I find the density matrix. If you don't agree, we can just plug in, right? To find it, of course, you use the equation I gave you earlier to do the inner product, right? But if you plug in, this is not difficult to check. 1, 0, 0, 1 plus alpha minus beta, and then negative or just beta minus alpha. Okay? Now you remember alpha plus beta equal to 1. You substitute into here, you will find that this is just equal to alpha 0, 0 beta. Okay? Try that. You run into a little bit troublesome. You think, oh, it doesn't look like correct. But you remember that alpha plus beta is equal to 1. So you do some substitution. You substitute this to here, so this becomes 1 minus alpha. And then so you cancel the 1 divided by 2, you get alpha again. Okay, just try it, okay? You trust me, this is what you have. Now, look at this. What is the expectation value? Or what is A in this case? A is what? Based on our definition, what is the magnitude of A? No, R is I plus A dot sigma, right? So what is the A here? A is 1 plus A dot sigma, right? So which is equal to I plus AX sigma X plus AY sigma Y plus AZ sigma Z, the whole thing divided by 2. Do we have sigma X, sigma Y? So they are all 0, right? And what is AZ? Yeah, so this is just AX squared plus AY squared plus AZ squared, right? The length of A, right? The length of the vector A. So this is just equal to alpha minus beta. Okay, so this is the length. So what does it mean? Think about this. In this Bloch sphere, I have 0 on top, 1 at the bottom, and this is the middle. If you ask me how much spin I have that is 0, it is like this is give me 1, right? Because pointing up. But you only have alpha part. I also have probability to give you -1 value, but it only has beta part. So the total has to be, I don't know, maybe that much, alpha minus beta, if alpha is larger. If beta is larger, then it will go down, right? So basically, and this one is just equal to A, right? So here I just use this simple example to tell you that A actually represents a mixed state. I don't know what I'm talking about. So A represents a mixed state that has the corresponding density matrix. So if I have a density matrix, right, you cannot put density matrix on the Bloch sphere, right? Just like in the pure state, you have a vector you put there, and then we say that if you have a density matrix with A equal to 1, then it corresponds to a pure state on the Bloch, the surface of the sphere. And here basically saying that if you have a density matrix, you have a mixed state, you have this A, right, which is less than 1. It corresponds to a mixed states that have the corresponding density matrix but give you the expectation value of that length. I think I am a little bit messy here. So let me write it again. Rewrite this one. I'm very sorry. This is a little bit, I should write down it. But really, really clear. Right, so with this, what I'm trying to say, so A represents the mixed state with expectation value A I'm sorry, representation value along a vector. Okay, so there's a vector coming from your density. So for a mixed state, right? You come up with sigma dot a dot sigma. For every mixed state, you come up with a dot sigma. So this A will be a vector in the Bloch sphere. And the magnitude of this A is the expectation value of that ensemble when you measure along that vector. Am I clear? Anyone understand? So, yeah, every density matrix gives you an A. And the expectation value of that mixed state is the length of A along A.
Sorry, where did you explain again where the alpha minus beta magnitude came from again?
Alpha minus beta here?
Yeah, where it's equal to the length, where did that come from again?
This one?
Yeah.
Because in general, I plus A dot sigma divided by 2, right? And the length of A is just the square, is just AX squared plus AY squared plus AC squared, take square root. But here, we clearly see that our AX, AY equals 0 because we don't have AX, AC, AX, AY, right? So that this is 0, right? So this is just equal to alpha minus beta. Because alpha minus beta is AC by definition. Okay? So I know it's confusing. Let me just say last word, and that's it. And then we continue next time. Let me say one more time. If you have an ensemble, you have a particular density matrix. From that density matrix, you will get the A after this expression. This A is a directional vector in our 3D space. If you do a measurement along this vector, for example, you put magnetic field along A, and the length of the A represents the expectation value when you measure along A. Use Z, sigma Z as example. Now A is actually pointing up. And the expectation value is going to be the length of A when you measure the spin in the Z direction. Okay. Think about that. Maybe I did not explain well, but okay, that's it. Thank you.